Greatest, if not the greatest challenges of our times is depicted on this graph, or the problem is depicted on this graph, or you have seen similar versions of this graph in many different sources. So we know that over the last decades, the temperature has been rising at a very high rate. And this has been caused by the increasing concentrations of greenhouse gases in the atmosphere. And different people, I mean, quite many are aware of it, and different people are trying to find different solutions. So I guess the most valuable here, and it's smart, as those that deal with proper science and engineering, they try to come up with new technologies for renewable energy, for storing energy, and maybe it's so far a bit less successful, but hopefully eventually it will work quite well for carbon capture to remove already emitted CO2. There are also very important social movements that try to affect our preferences and provide information that may lead to changes into maybe more sustainable diet and maybe general more sustainable approach to consumption. And then there are economists. And the economist solution to the problem is carbon taxation. So why a carbon tax? Because those of you who study economics in one of the first lectures learned about optimization principle. So all actions of an individual or of a firm are driven by this principle, so that we act such the marginal benefit of an action is equal to the marginal cost. So this is all individually rational individuals behave like that. And in the setting that we study, in the simple setting that we study in the beginning of our microeconomics courses, it also maximizes social welfare. But the statement is not true if there are externalities. And with all energy-intensive or fossil fuels-based industries, there are those externalities. So burning fossil fuels emits greenhouse gases. And the benefits of burning those fossil fuels are captured by power plants, while the costs are borne by others, especially future generations. So consider a fossil fuel power station. So the fossil fuel power station generates power, but it also emits CO2, which then causes, among other things, typhoons, droughts, which cause productivity loss, damages, biodiversity loss, and the costs are borne not by the power plants, but by the affected communities. So going back to this simple optimization principle, if a power plant, the power plant's problem is such that it burns coal in such a way that the marginal cost or marginal benefit from the extra unit of energy it produced is equal to the marginal cost of the fuel burned. But if you look at this from a social perspective, this optimization problem fails to solve the social optimum because, as we said before, we have this additional social cost of carbon. So the private benefits are lower than social costs of such an action. So from economics perspective, burning fossil fuels, it's not a bad thing in itself. We would probably optimally have a certain level of global warming, a certain a level of CO2 emissions in the atmosphere so that the temperature would be higher than the pre-industrial times. But there is no doubt that at the moment, or there's very little doubt that at the moment, we are burning too much fossil fuels. And taxation is best known to economists' way to restore the efficient allocation. So that would bring those social costs of carbon to those that actually burn those fossil fuels. And this is generally best solution to restore efficient use of resources on markets with externalities. But of course, it is not easy to design and to implement carbon tax. So there are quite many technical problems. So generally, what tax rate to choose? First we need to know what are the social costs of emissions. So as we know, a particle of CO2 stays in atmospheres for hundreds of years, so around 1,000 years or so. So we need to accumulate the costs of damage caused by this extra unit of coal for quite some time. How to assess those costs, how to, in our optimization today, take into account future generations. It's quite a complicated thing. Then we need to know, decide what to tax. Shall we tax production? Shall we tax consumption? And then once we get those tax revenues, there's also an open question, what to do with those resources. But then there are also problems of, I would say, political economy nature, so problems of implementation. So, well, general people or voters don't like taxes, and that's quite clear. And it was, in terms of climate taxation, it was, I think, very visible. Was a couple of months ago when the French government tried to introduce higher sort of climate-related taxes on petrol, which led to huge yellow vests movement in France and quite violent protests. And for this carbon taxation to be efficient, it should be implemented globally. And as you follow different UN-organized climate summits, you get quite a clear view that it is not feasible to implement such a solution globally. So there are some individual countries or groups of countries that try to unilaterally implement carbon taxation. So in Europe, and the European Union, we have the EU emissions trading scheme, so which is the largest carbon market in the world, so which is a form of taxation on fossil fuels or on CO2 emissions. But the problem of those unilateral approaches to carbon taxation is that they cause damage to productivity. So they increase costs of production of the affected firms. So which is especially a problem in energy-intensive, trade-exposed industries. So the remainder of the presentation will be based on my joint research with Hinek Nutzman from Hanover University about the impact of the energy-intensive, of carbon taxation on energy-intensive, trade-exposed industries. So, but first, let's talk a bit about why it is a problem. That what damage, sort of, I guess, conceptually, can carbon tax cause to those energy-intensive, trade-exposed industries? So we'll talk about commodities. Commodities such as petrochemicals, metals. So those commodities are widely traded internationally, which means that there are basically no cost differences. So in the prices of those commodities, the transportation costs are relatively low, so no matter where you buy a ton of coal or a ton of steel, you pay basically the same price. It doesn't matter if it's Bristol, if it's New York, or if it's Shanghai, the price is the same, or almost the same, because the unit transportation costs are relatively low. So, so consider that you are having a steel plant. So if you want to make a ton of steel, what you need is a bit of ore, 1.7 tons, a bit of coal, around less than 1 ton, and then a bit of labor and capital. And because of those narrow international price spreads, the costs of production were almost the same. It was only the labor costs and maybe some environmental regulations that were determining where to produce those energy-intensive commodities. But those costs, or as we call it, energy cost spreads, are widening, or set to widen. So the European carbon price has actually, over the last 12 months, has increased quite much and is set to rise up to 50 euros per ton of CO2 emitted, up to 5 euros just 5 years ago, and up from 0 10 years ago. So basically until the end of 2017, those carbon price was rather negligible. And so Europe is implementing, or has implemented, carbon taxations. Some other regions are following suit. California, China are the best examples. So what does it mean? It means those carbon policies are bringing change to international linkages. That under current regulations, the price spreads of those intensive commodities will remain low. So the price of steel, unless there are new regulations imposed, will remain the same in Europe, where there is regulation, and let's say New York, where there is no regulation. But the input spreads, so the costs of the effective costs of energy, if we include not only to the price of coal at the cost of emissions, will widen because of those carbon policies. So the key questions that I'll try to answer during this talk is, how do regional energy spreads affect market competition? And I will show how it affects global commodity prices, how it affects production relocation from one region to another region, how it affects profits of producers in different regions, and how it affects investment decisions. Another very important questions in this issue that I'll not try to address is how those regional sort of change in cost spreads affects employment, and how much it promotes innovation in fossil-free production technologies. So, I mean, it is quite a big problem. There's quite many people that are working in those energy-intensive industries. So it is hundreds of thousands of jobs that are at risk in Europe because of those regulations. So while implementing it, it's good to get an idea what damage it would cause to those industries, to the people working there. So as economists, you would like to try to assess what damage has been already done and what damage will happen in the future. But the problem is that there is very limited data. So when it comes to ETS, so this largest and the longest existing carbon tax system in Europe, well, it has been there since 2002, but energy-intensive, trade-exposed industries were exempted until 2013. And then afterwards, for a couple of years after 2013, so between 2013 and 2017, the tax rate, or the costs of emission allowances, so each firm that is in the system is obliged to buy emission allowances, so sort of a right to emit. And those emissions are bought on a market. So there is a market, so the price is set through competition for those emission allowances, but generally there is no difference effectively between that and exogenously set tax rate, at least for the problem that we are discussing at the moment. So, and since they were so low, it is very difficult to estimate any impact. So consider example of steel. So the price of steel in this period has been around 600–700 euros per ton, while the emission allowances prices were around 6 euros per ton of CO2 emitted. Given the emissions intensity of the steel industry, so you need around a bit less than 2 tons, or you emit around 2 tons of CO2 to produce 1 ton of steel, which means that in the years in which steel industry was in the system, the costs of emissions for European steel producers were only around 11 euros per ton. So this emission tax was less than 2% of the final product price. I'm not saying that there is no carbon tax, but given the general volatility in commodity markets, this little extra variation between the regional production costs imposed by the European carbon tax is rather not enough to get a robust results on the impact of the tax on this industry. And it is also quite dangerous to extrapolate from the small change in the production costs that occurred in this period to the large changes that we expect to happen in the future, or that we're actually already experiencing at the moment, because at the moment the emission costs in Europe, or the carbon tax, has increased around 30 euros per ton of CO2 emitted. So we want to know what is the impact of this carbon tax on the industry, but actually we can't really use the data from the period where this carbon tax was implemented in the industry, because we wouldn't get enough variation to get reasonable results. So we need to find a bit of different strategy. So what about using regional commodity price spreads? So I said that generally those regional commodity price spreads are quite low. But maybe we can find an energy commodity for which the prices, there were some regional price differences. Because from a power plant in Europe, it doesn't matter if the cost difference is driven by the difference in the sum of coal price and carbon price, or is it just a difference of regional coal prices? So let's have a look at the sort of first commodity one thinks of when we are talking about energy commodities, crude oil. So this plot shows European and US crude oil prices over the last 20 years. So as you can see, the price was quite the same. There's almost no differences between the regions. And there was this bit crazy period because of the so-called Midwest oil glut. Or this period was called Midwest oil glut. But generally, for our purposes, there is not enough of regional variation to get reasonable results. We would get, I don't have a plot for coal, but you would get a very similar picture. So, but there is some hope. Look at regional price spreads in natural gas market. Again, the solid line is natural gas price in Europe. The dashed line is natural gas price in the US. As you can see, there have been quite substantial differences in natural gas prices, in the regional natural gas prices. So what we'll try to do is to exploit the impact of those regional natural gas prices on energy-intensive trade-exposed industries that are using natural gas as the main feedstock, as the main component for production. So what natural gas is being used for? Well, we use natural gas to generate electricity. We use it for heating, and this is the largest part of natural gas use, but we also use for production of chemicals. There are some natural gas-based chemicals, and those include, the largest of them, the most economically most important are ammonia, methanol, melanin, and ammonia is by far the largest. So what is ammonia? Ammonia is a compound of nitrogen and hydrogen, and so it is a source of source of nitrogen for plants. So it is used as fertilizer. It's a plant nutrient that's used as fertilizer. And without ammonia and without nitrogen fertilizers, we wouldn't have modern agriculture. It is very much natural gas based. So the costs, around 90% of ammonia production costs is the cost of natural gas. It is quite a big market. So annually, with current prices, the annual production, the world production of ammonia is worth around 50 billion US dollars. And from emissions perspective, it's also a relatively important market because around 1% of greenhouse gases globally come from ammonia production. So first, let's have a look at the plot of ammonia prices. Again, solid line in Europe, dashed line in the US. I hope that this graph convinces you that the ammonia market has been quite integrated. The prices of ammonia in Europe and the US are quite similar. They have been almost the same, at least the trend has been very much the same. And throughout the whole period, the spread, the difference, the regional cost difference has been quite stable. So throughout the whole period, the ammonia price was slightly higher in the US, but the difference was very much stable. So we have studied quite a bit about how ammonia is produced, what are the production costs, what are the determinants of production costs, what is energy efficiency of ammonia plants around the world, and using some also literature on the topic, we're able to produce plots or calculate average marginal cost of ammonia production in Europe, in the US. So we have which is, as I said, natural gas is the main cost component, but not the only one. So we have been able to produce the marginal costs of ammonia production in Europe and the US. And those red lines show the production costs. So again, the solid line is Europe, dashed line is US. So for the first period of between year 1996, I think, and 2008, we could see that the world ammonia price. So first, we could see that before 2008 there were some spikes. In 2000, in the winter of December of 2000 was very cold in the US. Since natural gas is used for heating, that's why there was quite a price spike in this period. And do we see a response of the global ammonia price to the cold winter in the US? Yes. Indeed, you could see that in this period there is a spike in ammonia prices as well. Then 2005, The great tragedy, the Katrina hurricane that destroyed natural gas production facilities in southern US. Again, quite a price spike in natural gas prices. Do we see spike in ammonia prices in the same period? Yes. But then, because as a simple macroeconomic theory predicts, on those oligopolistic markets, or what the sort of Cournot model would predict, that the price on this oligopolistically competitive market should be a weighted average of production costs between the regions. And that's exactly what we see until 2008. And then, what is in 2008? That's where the shale boom starts. There's huge resources of natural gas being discovered in the US. And the price drops in the US quite significantly. While in Europe, there was no such discovery. There were no facilities to transport natural gas from the US to Europe. That's why natural gas prices remained high. And as you can see, this shale gas, judging from this period up to 2008, drawing our intuition from the Cournot model, you would expect that the regional cost decrease should have some impact on the global prices. So regional cost decrease in a major producing region should have some impact on global prices. But it didn't have impact at all. The link between the US production costs and the global price of ammonia decreased or stopped completely. So what lesson can you draw from it? So first, or just to sort of recapitulate, up to 2008, regional price changes were shaping ammonia price. But then shale boom happened, and the decrease in natural gas price in the US did not translate into into global ammonia prices. So does it mean that it's only price increases that are passed through into prices? Is this result at odds with economic theory or with Cournot model? Well, let's first have a look at quantities. Maybe the changes in quantities would help us to understand it better. Because the price can decrease only if the change in costs goes together with reallocation of production from the high-cost region to the low-cost region. And what do we see? So this graph here shows regional annual ammonia production in the US and in Europe. Again, solid line Europe, dashed line US. And what do we see? Up to 2008, there was a bit of a decreasing trend in both regions, but the production was quite sensitive to the cost advantage, regional cost advantage. So this bottom part of the plot shows marginal cost gap. So the difference between the European and the US ammonia production costs, annual average. So here in 2012, the costs of producing a ton of ammonia in Europe were around $300 higher than producing the same quantity of ammonia in the US. So what do you learn from those two graphs? So look here, year 2000, cold winter in the US, it becomes relatively more advantageous to produce ammonia in Europe. And what do we see? Well, production in Europe increases, production in the US decreases. Then again, 2005, remember, there was this Katrina-related price spike. So again, this small dip shows that it becomes more profitable to produce ammonia in Europe relatively to the US. And what do we see? we see again that production in Europe jumps while the production in the US decreases. And then comes the shale gas. We would expect that there is like an enormous amount of ammonia being produced in the US given the cost advantage that has never been experienced by the US producers. But is what we see? Not really. Yes, there is some positive situation. Production increased, but it reached its capacity. US producers were closing their plants. So before 2000, production, it was a higher level of production as possible than with those advantageous gas prices, because quite a large number of ammonia production plants was closed, and the US producers were simply not able to increase their production. So before 2008, this relative price changes led to production relocation. So our estimates show that approximately $10 relative price change, or around 5% of cost change, led to around 1%, to the relocation of around 1% of production from one region to another. But again, this relation ceased in 2008. US producers reached capacity constraints and they couldn't respond any further. So it is this short-term capacity constraints that destroyed what we'd expect from a standard competition model. So what does this mean? They couldn't, US ammonia producers, they couldn't produce more. But as we could see here, they were making quite a lot of money on production of that ammonia they actually were able to produce given the capacity constraints. So we should expect that that the shale gas boom maybe was not reflected into ammonia prices, but should be reflected in the profits of the ammonia producers. I mean, we don't have good data on profits. The data on profits are, well, there's also accounting profits that contain many other things, but, well, profits should be reflected into the market valuation. So we have constructed portfolios of the European and the US ammonia producers. And the solid line here shows the ratio of those two portfolios. So here, for instance, means that in year again around 2012, the rate of growth of the portfolio of the US ammonia producers, which contains all US ammonia producers. So the rate of growth from year 2005 to year 2012 was 2.5 times higher than the rates of growth or the growth of the portfolio of the US of the European ammonia producers. That the investment in the US ammonia producers was 2.5 times as profitable as investment in the stocks of European ammonia producers. And interestingly, how this portfolio return ratio is shaped very much reflects the difference in marginal costs between the two regions, between US and Europe. So it shows that, well, it is the plant owners in the cost-advantaged region that capture the entire rent, the entire benefit from low natural gas prices in that region, or low relative production costs in that region. So we can translate this intuition into the effect of a carbon tax, because what the carbon tax would do would again would here create this cost gap between the two regions. And if the producers are capacity constrained, they cannot increase the production further, then this carbon tax in one region would be just a gift to producer in the region that do not implement such a tax. So now, let's have a look at the plot of investment and disinvestment decision in the US. So the solid line here, as before, shows the marginal cost gap. So again, the difference in production costs between Europe and the US. While the vertical lines show data points in which there was announcement of a disinvestment decision, so closing an ammonia plant in the US. So those are the red lines. Or starting a new ammonia plant. Those are the green lines. So as you could see before, those early 2000s, it was this dark age of the US ammonia industry. In this period, US was not very competitive. Firms were on average making losses, and we could see this wave of ammonia plant closures. So during this period, around, I think, if I remember correctly, 11 plants were closed, altogether 6 million metric tons of annual capacity, which was around, I think, 25 or 30% of ammonia production capacity in the year 1996. Well, it's not strange. You're making losses?
What are the green dots lines?
I will go there in a second. I mean, it's not strange. You're making losses. You don't see very much anything good happening in the future. We don't want to make losses anymore. We just close the plant. But then this miracle happened. This huge natural gas discovery, or discovery of the technology that allowed to release this natural gas. And suddenly, it became super profitable to produce ammonia in the US. But do we see new plants not only being built? So it's not. So the green lines show investment decisions, or it's not where the plant goes online. It's just when it is announced that a new plant will be built, and this is this credible announcement. So we here included only the announcement that led to investments. So not all of those. So here, those green lines are points where it was announced that a new ammonia plant will be built, and this plant, as of, I think, January 2019, was either built or was in advanced construction process. So there are quite many announcements that then did not materialize. There was this sort of such a boom that everyone who had more than $100 in his or her wallet wanted to announce to build a new ammonia plant, but quite many of those the announcements were not very credible. So those dashed lines, or the green lines, they mean greenfield or brownfield investment. So there was you start from scratch or add new capacity to an existing plant. So just expand the existing plant. The dashed lines, this is restarting of a previously idled plant. So of those red lines, not all of them were just completely scrapped, idle. So just sort of, I don't know exactly how they do it, but there is a way to, at a high cost, but to rather than just closing a plant, I mean just removing all the machinery, we just let it wait a couple of years. And then if conditions are favorable, we restart it. So we see that there was this huge gap that opened, and only 2 or 3 years later, there's first this low-cost ways of expanding the capacity in the US. There were just those restarts of mothballed plants, and only 4 years after it became really profitable, US ammonia producers made those credible decisions to build a new plant. So it takes a really long time from seeing that there is a profit opportunity to understand that this is a long-lasting opportunity that will allow to recover the investment costs required to build a new plant. So, as I said before, yes, this new capacity is necessary for the local cost decrease to impact prices. So because we need more production to affect the prices. But in those capital-intensive industries, things really take time. So for ammonia, it is around 7 years from the moment you plan to when, or maybe 7 years, to the moment the plant goes online. But it even takes time, as you see, it takes time for firms to plan those plants. Well, because those profits that you get, they must cover this upfront investment costs, which are quite high. So for ammonia, it's around $1,500 per ton of annual capacity. Given that ammonia sells at around $300 per ton, which means that even when you have zero costs, it takes you 5 years to get this money back. And you get this money only from this gap. When you're not, when your costs are equal to the market price, you're not making profits at all. Yeah, so if the gap is not large enough that there's new capacity being built, then, well, there are some new capacity coming, but only at the rate that this old capacity is dying, more or less. So actually, I don't have here the plot for Europe, but if you would plot it, you would see that in this period, there was one or two, I think no, 2 or 3 plant closures in Europe, and there was one new plant being built, but built by Czech Prime Minister in Slovakia, which is the most landlocked country, which, given the relatively high cost of land transportation of ammonia, is a bit understandable. And then, so yes, so things take time in capital-intensive industries, and the policy uncertainty slow things even further. So just to sum up, I promised to talk about carbon tax, while I was talking only about natural gas prices. I sort of was trying to convince, but maybe I didn't put enough effort, that actually it is possible to draw lessons from the ammonia market on the global problem of carbon taxation if in natural gas markets. Why? Because this carbon tax is opening the regional price spreads. So exactly the same what we saw in ammonia market, even in absence of the carbon tax. So what lessons do we see? Well, we see that this carbon tax would sort of kills production in the less advantageous region, but only softly. So the change doesn't happen immediately. It takes a really long time, but sort of slowly it occurs. And does it lead? So the important question to ask is if it leads to emissions reductions. So let's try to translate what we learned from this ammonia market to this reverse situation that is not a cost decrease, but a cost increase. So we'd see that in the short run, the taxes would increase global prices. So if there is not enough spare capacity elsewhere, so that it could completely replace production in the region in which we have carbon tax, the global prices would increase at a rate relatively close to the tax rate. So there will be, in the short run, it will be quite a high pass-through of carbon tax into global prices. So this increase of the global prices, of course, if there is some demand elasticity, would decrease demand, the quantity demanded would decrease production. So there would be a bit of decrease in CO2 emissions because of the higher prices. But probably, at least in ammonia, The demand is very inelastic. It's all driven by, the demand for ammonia is driven by demand for food, and we can't really eat less. I mean, maybe some of us can. It should, but generally speaking, I mean, it's a bit problematic. There are limits to how much we can decrease it. And in the short run, those with the carbon tax that opens the cost gap would benefit mostly or almost only the producers. So there will be little impact on emissions and huge impact on profits of the producers located in other regions than the region that implements tax. So as I said, if there is the spare capacity elsewhere is low, it's not possible to increase production elsewhere, then this, the impact of the carbon tax on production relocation will be quite low. So in that case, even large tax may not have a strong impact on the competitiveness in the short period. If you are talking about a situation that this is a relatively competitive market, we have US and Europe that are producing at the same costs, they're all making zero profits. So when you implement this carbon tax in one region, the region with the high tax continues making zero profit, while the region without a tax now have a profits proportional to the level of tax. But this is only in the short run. So in the long run, there is carbon leakage. So once plants die in the region of the tax, they're not being rebuilt in the same region. They will be moved to the region that doesn't have this carbon policy. So in the long run, we would expect complete carbon leakage. So the production completely moving to the region without the tax. And in the long run, there would be absolutely no impact of a local carbon tax on global prices or global production levels, only on the place where the production takes place. So what we need to reduce emissions, we need some breakthrough fossil-free technologies. And given this relatively short-lived impact of unilateral carbon taxations, those taxes may not provide sufficient incentives for research and development required to produce such technologies. I mean, there is a bit of consolation that these new facilities that are being built to replace the old capacity, construction of which is slightly accelerated because of regional carbon tax, they are slightly more energy efficient. So we see a bit of per unit emissions, per unit of production emission reductions, but it's definitely not enough, not what we need if you want to limit the temperature increase to a reasonable 1.5 degrees level. So thank you very much. This is the view of ammonia plant from the top of a urea tower. Urea tower is a thing that you make out of ammonia to actually put on the fields, which is during our study trip in Police in northwestern Poland. So thank you very much.